Hello and welcome to today's lesson on positron decay. In today's lesson, we will begin by exploring the properties of positron decay and the types of nuclei it typically occurs in. We will then learn to represent positron decay using a nuclear equation. So far, we have delved into the atomic model and the fundamental nature of radioactive decay. You have learned about the structure of atoms, the different types of radiation, such as alpha and beta minus radiation, and their associated nuclear equations. Building on this foundation, we can now explore positron radiation in more depth. This lesson will enrich our broader understanding of nuclear processes, stability, and the transformations that occur within atomic nuclei to make them more stable. Let's get started. Positron decay, sometimes referred to as beta plus decay, is the second type of beta decay. During positron decay, an unstable atomic nucleus emits a positron, a particle that has the same mass as an electron but carries a positive charge. You can think of a positron as the electron's positively charged cousin. Positron decay primarily occurs in proton-rich nuclei. These are atomic nuclei that have too many protons compared to neutrons, which leads to instability. To regain stability, the nucleus undergoes a transformation. Inside the nucleus, a proton is converted into two particles, a neutron and a positron. This conversion is crucial because it reduces the number of protons in the nucleus, addressing the proton excess. The newly formed positron is then emitted from the nucleus. As a result of the proton to neutron conversion, the atomic number of the element decreases by 1, since the nucleus now has one less proton. However, the mass number remains unchanged because the total number of nucleons, protons, and neutrons stays the same. By converting a proton into a neutron and emitting a positron, the nucleus moves toward a more balanced proton to neutron ratio, which is essential for nuclear stability. Now that we understand what positron decay is and why it occurs, let's see how we can represent positron decay using nuclear equations. We begin by identifying the nucleus sodium-22. This isotope has a mass number of 22, the total number of protons and neutrons, and an atomic number of 11, the number of protons. During positron decay, a proton in the sodium-22 nucleus is converted into a neutron and a positron. The positron, which is the beta plus particle, is then emitted from the nucleus. Our next step involves mass and atomic number conservation. The mass number remains the same at 22 because a proton is converted into a neutron, so no mass is lost or gained. The atomic number, however, decreases by 1, changing from 11 to 10 because the nucleus now has one less proton. Now we can identify the new nucleus. The decrease in the atomic number by 1 means the new nucleus has an atomic number of 10. Referring to the periodic table, the element with an atomic number of 10 is neon. Thus, the new nucleus is neon-22. We can now write out the representation of positron decay. In nuclear equations, a positron is represented as shown on the whiteboard. The subscript +1 represents its positive charge, and the superscript 0 indicates its negligible mass compared to protons and neutrons. Therefore, the nuclear equation can be written as Na22 decays into Ne22 with the emission of a positron. Let's apply what we've learned to a few more specific problems regarding positron radiation to consolidate our understanding. Here, we're being asked to write the positron emission equation for carbon-11. First, we identify the initial nucleus and its properties, which is carbon-11, with an atomic number of 6. Then we determine the changes after emission. When carbon-11 emits a positron, one proton in the nucleus is converted into a neutron. From this, we know the mass number stays the same at 11, but the atomic number decreases by 1 from 6 to 5. With this information, we can identify the new nucleus. The element with atomic number 5 is boron, hence the new nucleus is boron-11. All that's left is to write the nuclear equation, which is C11 becomes B11 plus a positron particle. Let's try one more. We need to write the positron emission equation for potassium-38. We start again by identifying the initial nucleus and its properties. In this case, potassium-38 with an atomic number of 19. We then considered the changes after emission. When potassium-38 emits a positron, one proton in the nucleus is converted into a neutron, so the mass number stays as 38. However, the atomic number decreases by 1, becoming 18. Now we can identify the new nucleus. The element with atomic number 18 is argon. This means the new nucleus is argon-38. With all of this information, we can now finish writing the nuclear equation, which is K38 becomes Ar38 and a positron particle. In today's lesson, we explored the properties and formation process of positron radiation, a type of beta decay. We learned that positrons are positively charged particles with the same mass as electrons, but opposite charge. We understood that positron radiation occurs in proton-rich nuclei, and how during the process, a proton in the nucleus is converted into a neutron, releasing a positron. We recognize how this helps the nucleus achieve a more stable ratio of protons to neutrons. Finally, we examine the nuclear equations representing positron emission. By understanding these nuclear equations and the role of positron emission, we gain insights into the mechanisms of radioactive decay, nuclear transformations, and the principles that govern atomic structure.